Hej och välkomna till dagens disputation där teknologilicentiat Per Boström-Rost ska försvara sin avhandling Sensor Management for Target Tracking Applications. Mitt namn är Gustaf Hendeby och jag är ordförande för disputationen. Jag är lektor här i reglerteknik vid Linköpings universitet och har också varit Pers huvudhandledare under disputationsarbetet här. I'll now switch to English and once again welcome everyone to this PhD defense where Licentiate of Engineering Per Boström-Rost is going to defend his thesis Sensor Management for Target Tracking Applications. My name is Gustaf Hendeby and I'm an associate professor here at Linköping University in automatic control, and I've been appointed the chairman of this event. I've also been the supervisor of Per during his PhD work. I have been had help from the co-supervisor, Prof. Daniel Axehill, in doing this.
Good afternoon.
And he's also from the automatic control division here at Linköping University. Okay, so with all that handled, now I'm very pleased to introduce the other main actors today. So first of all, we have the faculty opponent, Professor Peter Willett from Connecticut in the United States, who will help us evaluate Per's work, discussing it with him. We also have a grading committee consisting of Professor Lennart Svensson from Chalmers University in Gothenburg, and Professor Peter Ögren from the Royal Institute of Technology, KTH, in Stockholm, and Professor Valentin Polishchuk from the Department of Science and Engineering in campus Norrköping of Linköping University. If something should go wrong here during this event, we also have a reserve for the committee. That's Professor Jan Åslund from the Division of Vehicular Systems here at Linköping University as well. So that's all the main people involved today. The procedure is as follows. First, the opponent, so Professor Willett, will give a general introduction to the field that Per has been working in, and that will be followed up by a presentation from the candidate, Licentiate Boström-Rost, who will then present his contributions in this field. Then we'll have a short break, and after that, the opponent will lead a discussion with the candidate about the thesis work, and that way evaluate it. After that, the committee will get a chance to ask questions that they might have to clarify the work. And after that, I will open up the floor for questions from the audience. Please use the Q&A function for that, and we'll communicate the information to Per. Once this is over, that marks the end of the public part of the defense, and the committee will retire to make a closed session decision about the grade of this event. So it will be either pass or fail. And the opponent and the supervisors will be present at this as well to answer questions. And once we're done with that, we'll return to this meeting again and give you the results. Before we continue, I would like to take the opportunity to thank Per Vispo-Nibel, who is managing all the technical things in the background here. I would not feel as comfortable in this situation without him. And I also would like to point out that we are recording this event so that you know that. Okay, so before we start, is there anything that you would like to add before we continue? Okay, good. Then, Professor Willett, the floor is yours.
Hello, everybody. I'm Peter Willett. I'm University of Connecticut. I've been selected as a faculty opponent. It's about 8:50 in the morning here, and it's a lousy day. I'm interested in the word opponent, by the way, because it sounds, I know that Swedes speak English better than we do, but opponent sounds so adversarial. And in fact, it's an unfamiliar role to think about somebody who's actually trying actively not to let somebody get their PhD thesis. And I can't say I feel that way, but I did take a fairly close look at the thesis and the contributions and have some comments on it. I've made realize I may be already talking too quickly, so slow me down if I am. I've made a short presentation. It's actually a PowerPoint deck. I think perhaps the first 7 or 8 slides are probably the first part, and the remainder refer to what we might talk about during the opponent section of this event. So let me try to go back to my screen. So just there, talking a little bit about target tracking, which is the basic segment to this. And if I understand correctly, by the way, I hope I'm not doing this wrong. I think that I was asked to give a background area that might be at a high level, background talk that might be at a high level, so that people who aren't necessarily, smart people who aren't necessarily involved in this would understand something about the background. Anyway, target tracking is dynamic estimation. It's where you have a process that is moving generally according to a markup process that's actually hidden. The underlying motion of what you're trying to track, which, hey, it could be a missile, torpedo, submarine, something like that, or it could be a car, is moving in a way that where the present location of it, based upon all the past information is typically the same as the same prediction you would get of the present location based upon only the previous sample. That's the markup process, and there's a noisy observation that comes from it. So dynamic estimation is or filtering is the process of trying to estimate and predict where the object, the target, is. Data association is part of target tracking, as is filtering. Filtering is if you know what the measurement is. Data association is if you don't know what the measurement is, and typically you might have several measurements that are to choose from. And then there's another component called track management, which is trying to tell how many targets are out there. I've sketched a little plot over there, which I sometimes use to try to explain the complexity of target tracking to people. And if they'll excuse me here, let's suppose, can you see my cursor, by the way? Is that visible?
Yeah.
My finger? Okay, so if you see an initial probability distribution density function, or a location of where you think the target is at time k, well, you might have 2 measurements at time k plus 1. And a typical thing to do is you might say, well, it could be here or it could be here. This could be the true measurement, or this could be the true measurement, or in fact, neither at all. Then you might have another measurement coming in, and in which case you don't actually get a lot of simplification in this, but you would say, well, either this comes from this measurement comes from this history, or this measurement comes from this history, et cetera. It's a complicated thing. And it becomes more complicated when there are false alarms, misdetections, and when there are multiple targets. Track management just says, okay, if I've got a stream of measurements coming in, do they make sense enough to say that actually is a target that I want to be tracking? There's a number of approaches to doing all those things, and the first 2 chapters in the thesis do a fairly good, concise job of sketching these. It's an unusual way to structure a thesis for me. I assume it's common at your university, but I liked it. This thesis concentrates, as I said, on an important ancillary part of target tracking, not one of the 3 I talked about there. So in this case here, if you have the opportunity to, I guess, manage, to design your sensing system, to get measurements, so you get a measurement over here or a measurement over there, how should you do that? How should you send out your sensor, let's supposing it's mobile, or even how should you schedule a dwell if it's not mobile, in order to get information that is best useful for the target or targets that you have. I've kind of stolen a picture here from the internet, tried to give credit to it, to try to give an idea. In this case here, it's I guess a Purdue thesis. You can see there are 3 targets. And in this case here, the sensor is actually doing kind of a circling tour, mostly over target number 2 and ignoring target number 1 and 3. But I think you can kind of see that it's a complicated problem, because should the sensor go and explore all 3 but do a poor job of it, or should it concentrate on 1? Well, good questions. All the elements of target tracking come into play at this point. The filtering, particularly to do with the criterion that you're going to be using to design your sensor management system. The data association. I've mentioned there unresolved targets. I'll come back to that later on, but only really right at the end. And the track management, because you will need to do 2 things here. You need to maintain old tracks, extant tracks, but you also need to find new ones if there are some coming in there. There are there's some key aspects to sensor path planning or management. There's generally a single criterion of goodness. And I've written down here, there are, I've written mix these elements. I guess I shouldn't have said that. There are typically elements of the energy expended on sensor motion, let's say, and on the quality of track. And there's a way you need to transform these such that you have a single criterion of goodness you're trying to optimize over. There's a question of what your time horizon ought to be. Do you simply go for a greedy approach where you put your sensor located in such a way that it's going to do the best job next scan, or do you try to reason out 6 scans? Clearly, the further you look out, the more difficult it's going to be. Target modeling, and in particular, I wrote down here, do targets have a goal? That actually isn't here in the thesis very much, something I'd like to stress a little bit. If there is a goal or a destination for a target, that probably should go into the mix. Sensor mobility, there are obstacles for sensors moving around. There are limits on how fast they can accelerate. And there's the cost. There's an aspect of this to game theory, because a target knows that it's being tracked and may try to do the most stealthy thing to avoid being tracked. Countermeasures is part of the same thing there. I've written down electronic countermeasures, such as range gate pull-off, other things like that. That isn't treated very much here, and I really wouldn't expect it to, but it's something to think about when you're dealing with any kind of a practical target tracking problem. Stealth, and in this case here, stealth I'm talking about of the sensor. The sensors are often high-value sensors. That's sort of a US military term, but it refers to something if you have a UAV, you really don't care all that much. I mean, you do, but not a whole lot if it gets blown up. On the other hand, if your sensing platform is a submarine, you do. And in a lot of cases, you want to be able to remain stealthy you want to track while remaining stealthy from the thing you're tracking. Multiple targets, that's something I sort of alluded to in the previous little stolen figure there. You either need to divide time between the targets, or you need to just say, I'm going to give up on some of these targets. And it becomes much more complicated when there are multiple sensors. And that's really only treated, I think, in the last chapter here, but it's a huge problem. And are they cooperative or not? That's mentioned in the thesis in chapter 6. It's a very thorny problem if they're not. I just noticed some things that I've seen previously here that I wanted to talk about in terms of sensor management. I remember some papers, oh gosh, it's going back 20, 25 years, in the Georgia Tech Research Institute benchmark problem. Dale Blair is the kind of the prime force behind this. I know he's one of your co-authors. The benchmark was a benchmark is sort of a common bake-off testing idea. And they had a suite of programs, they're actually open, you can get them, where some of them are, where a target was being tracked by a radar, and there were 6, I think, scenario trajectories that they had, and the goal there was to not to get good tracks, but not to lose the targets. It was actually kind of a news to me that people practically didn't even care all that much about how good the tracks were to a large extent, but they really just simply did not want to lose the target, because it's very hard to reacquire a target once you've lost it. And for example, one of the things they found, and you wanted to minimize, one of your criteria was minimizing the radar dwell time, and the other was the radar energy. You didn't want to you would not burn it out. A good solution was to schedule a radar dwell, when the predicted uncertainty in the target exceeded about a quarter of a beam width, which is an interesting thing, but it's kind of a rule of thumb that people tend to use. I remember also there was some work from information-based, and when I say information, I mean in the sense of the information matrix, information-based planning, similar to what's being done here, I think. One of the aspects here, which is alluded to in this thesis, but is perhaps, I think I would like to see more explicit, is that in talking about radar, the resolution cell eccentricity is greater than 100 often. When I say eccentricity, I mean the resolution cells look like pancakes. Hope that's a common word. Where the downrange resolution might be the order of a meter or a few meters, but the cross-range resolution, as you get out to fairly long distances, might be the order of kilometers. There's also an aspect-dependent radar cross-section. Again, I'm focusing here on radar, but in a number of situations, particularly with stealthy targets, you end up with kind of a strobe effect, as that for certain aspects you can see it blindingly, and others you can scarcely see it at all. There is, in practical radar dwell scheduling, I've seen some work done by the Raytheon people here, where there's always a mixture between the track dwells and search dwells. Again, I'm focusing on radar. I apologize if that's not what you want to do. So a track dwell is when you might go spend some time looking for the targets you got out there, and then you multitask and go look at the horizon to see if there's a new target out there, and you try to cover the horizon. That's similar to some of the stuff we see in the later chapters in this paper. Target spawn, also an issue, and that's not treated here, and it actually probably is something to look at in the future. Practical targets of people's great interest are targets which give rise to other targets. That can be things like a submarine launching a torpedo or a missile turning into multiple warheads. Very important. So you can also use, and I wrote this down before I got to this later in the thesis, but you can also use the spoiled beam for wider searches, meaning that you could use a very accurate small resolution cell if you're trying to get accurate target track. On the other hand, you might want to consider using a big fat resolution cell, a lousy range resolution and a much wider beam if you want to do a wider search to look for something. And that is alluded to in one of the chapters. I think it's C or paper C or D, I can't remember which. Do you want me to say this here? I got an overall impression to write. I can do this later. I think probably it's right, man. I think it's a sound piece of work. It's tight. I'm fond of the layout. At UConn, our theses are usually basically reformatted papers. They're almost a formality. You put them together. You get published papers. You put them together into a thesis. You have some introduction and some conclusion, and the real arbiter of whether you're going to get the real criterion of whether you're going to pass or not is whether these papers have been published, have been found to be reviewed to be good. What I like here is the introductory chapter is very interesting. Nice discussion about the contribution of future works in a concise form. I want to compliment the candidate here particularly on what he does, something which I really like in all the papers, and I sometimes find it lacking, and I get really super frustrated. He really clearly lays out the model that he's using for the target, for the sensor, and he lays out his modeling assumptions, and I can find them. And that's, sometimes people seem to think that's not very important, and for me, there's nothing more important. The published record is good. He's got two published papers, lots of conference papers. Citations are a little low. I don't think that's his fault. It's kind of recent. Also, the area. I mean, if you were doing a thesis in machine learning, you'd probably have 2,000 citations after the first month. Target tracking is an area where people move kind of slowly and where there's not the feverish activity there is in those areas. Do you want me to discuss the specific contributions in an overview fashion?
You could if you want.
You could if you want, yeah, sure. Go ahead.
Okay, I just want to talk about these 6 papers here. So the first paper was almost the most exciting one here, the paper number A here. It was discovered that when under the, again, the modeling was great. I had to go look back at it and found out I'd skimmed over what I should have looked deeply at. We have a number of targets where at known locations, and each target had something going on there, some kind of a feature that was moving around. And there's a limited field of view of the sensor. And it was proven that this could be turned into a convex problem, which to me is huge. It's a very interesting problem, interesting characteristic. It means that if you find a stationary point of your optimization algorithm, it's going to be optimal. It's going to be the global optimal. That's great. It was expanded upon in the second paper there, where the observations were accumulated, but the sensor was worried about being tracked by an adversarial tracker as well. So there was an overlay to that, which is kind of nice. There was another paper where the sensor management was sensor management is fairly well understood if you have a linear Gaussian model, but that's not really the interesting model. So if you have something with nonlinearities, and if you have something with some sensors with limited fields of view and things like that, then it's not well understood. And the concept here was to use sample paths, to use samples of what possible future trajectories would be. Worked out kind of nicely. There was a paper, this is the one with Blair, I think, if I remember correctly, yes, where I gather it was suggested by Blair at an aerospace conference to take a look at this, where there was exactly the kind of trade-off I'm talking about of using a spoiled beam. If you use a spoiled beam, of course, if you use a big fat resolution cell, then you reduce the accuracy of your track, but you don't lose the track so easily. And there's a trade-off here. And the question would be, as is explored by alpha beta filter analysis, what would be an optimal place, an optimal setting for the parameters of range accuracy and beam width. So the last two papers were rather different. In this case here, we used a multi-Bernoulli filter with a Poisson birth process overlaid to it. And there was a sensor management system which was based on rollout, which I find a very underused and very intuitive optimization topic. That did a nice job of splitting duties between tracking targets which are already there and searching for undetected targets and targets that are just being born. There was a further paper, which I think is only under review, where this was augmented with the idea of, really simplified, with a gridded uniform distribution for the undetected targets. And then it was extended to multiple targets and to multiple sensors too. I didn't write that down. And I think that's where I was going to end. Is that okay?
Perfect. Thank you very much for a thorough walkthrough of the field and the contributions. Per will now.
So I'll continue on what Professor Willett was talking about and try to highlight the main contributions, or at least what I see as the main contributions of the thesis. But before starting, I'd like to thank our sponsors, both Saab Aeronautics for letting me do this during working hours, and the Wallenberg AI Autonomous Systems and Software Program for providing the funding. So the topic of the thesis is sensor management, which is automation of sensor control systems. And the whole point of sensor management is to decrease the operator workload and to increase the overall sensor system performance. And if you think about a sensor system and you have a sensor management component included, the operator doesn't have to control each and every sensor individually, but instead supplies high-level commands to the system to instruct the system about what the overall goals of the mission is or are. And then the idea is that the sensor management component handles the low-level feedback control of the sensors. So the contributions are all related to sensor management and can be divided into three categories: optimality guarantees in informative path planning, optimized tracking of maneuvering targets, and planning for multiple target tracking. It contains 6 papers, out of which 5 are published and 1 is still under review. And in this talk, I'll go through the contributions in each category one by one, starting with optimality guarantees in informative path planning. So the problem that we're considering here is that we have a mobile sensor with a limited sensing range, here illustrated by the aircraft in the black circle. And the mobile sensor is operating in an area where there are features at known locations. So the features here are marked by the plus signs. And we assume that we know where the features are, but that each feature has an unknown associated quantity of interest, which you can think of as, for example, the air quality or the temperature at the corresponding position. And the mobile sensor can obtain measurements of these quantities of interest if it's located close enough to the features, that is, if it's located within the corresponding green regions. This red area is then an adversarial sensing region where if the mobile sensor is located within this red area, an adversarial observer is able to obtain measurements of the mobile sensors. The task that we're considering, or the problem, is to plan a sensor path that maximizes the information that we gather about these features while avoiding to let the opponent or the adversarial observer obtain measurements of the mobile sensor. That is, we try to maximize the stealth behavior. Formally, we can formulate this as an optimization problem: maximize stealth and gathered information subject to a number of models, which tells us, well, how the features evolve over time, how the sensors are able to obtain measurements, and how information is accumulated given multiple measurements. And I won't include too many equations, but I figured this one is fairly important, so I chose to include it. So here, this is the mathematical definition of the informative path planning problem I'm talking about. So you can see that in the objective function, we have a measure here on how well the stealth aspect is treated. And this component treats the information gathering part. And these models are formulated as constraints in the problem formulation. And the optimization problems of this type, mixed binary optimization problems, are in general quite challenging to solve, to say the least. And in particular, this formulation includes nonlinear equality constraints, which in practice makes the problem intractable. And the contribution that we have here is that we've showed that, well, you can actually replace these nonlinear equality constraints with generalized inequality constraints, which nicely turns the problem into a tractable optimization problem. So just to summarize the contributions within this area is that we've showed that under certain assumptions you can solve informative path planning problems to global optimality or to any user-defined certified level of suboptimality. Moving on to the next category, optimized tracking of maneuvering targets. And the problem that we're considering here is the following. So we still have a mobile sensor with a limited field of view, but here the targets are no longer static. Instead, they're maneuvering. And the task is to maximize the tracking performance, well, some measure of the tracking performance. And I'll talk about two different approaches to this problem here. The first one corresponds to planning the sensor trajectory based on predictions of where we think the target will end up next. So let's say that we know that the target currently is located down here with a velocity vector pointing towards the upper left. Then based on a model of the target motion, we can predict its future trajectory. And we can say, well, we don't know exactly where it will end up, but with some certainty it will be located within this region here. And the most likely trajectory is that, according to the model at least, it is that the target continues with its current velocity and follows a straight path, basically. And the baseline planning method is then that we plan the sensor trajectory based on this trajectory only. And I'll show you a short animation of what happens when you do this. So here you will see the sensor in the gray dot, and the field of view is in blue, and the estimated target trajectory is in orange, while the true target trajectory is in black. So initially it works out fairly well, but then eventually the target starts maneuvering, and at some point the actual target ends up outside of the field of view. And then we don't get any new measurements, which means we can't update the state estimate with more information. And what happens is that the actual target turns to the right, and the sensor basically continues to track a ghost target to the left. So that clearly doesn't work as expected or as desired. So what we proposed is to use, well, instead of considering just the most likely trajectory, we can consider a whole bunch of candidate target trajectories, including, for example, some where it turns to the right and some where it turns to the left. And then we compute the sensor trajectory which performs well for all of these candidate target trajectories. And this results in a much better tracking performance. As you might see, the sensor maintains a slightly larger distance to the target, which allows it to adjust its trajectory if the target maneuvers. And thereby we avoid losing track of the target, which is nice. So there is clearly a connection between the tracking range, that is the distance between the sensor and the target, and the tracking performance. And that brings us to our next approach, where we try to optimize the tracking range based on, well, an assumption of what we think is the maximum acceleration that the target can perform. And in tracking problems of this type, there is a dilemma. So if we increase the tracking range, the risk that we lose track of the target decreases. But at the same time, the measurement quality decreases as well, so the tracking error increases. And the question is, can we find the optimal trade-off here and find the tracking range that yields the smallest possible tracking error, given that we're willing to accept probability of track loss at a certain level? And it turns out that we can. This figure is to illustrate why it's important to keep a large enough distance to the target. Let's say that we are tracking the target at a very short range. Well, then it performs a maneuver, and the risk that it ends up outside the field of view is very large. But then again, keep in mind that you would like to be as close as possible in order to minimize the tracking error. So these are some plots from Monte Carlo simulations, where the target first travels straight, then performs a maneuver with maximum acceleration, and then again continues on a straight path. And up here you see the tracking error, and you see that the orange curve is, the orange choice of tracking range gives a low tracking error. But as the target maneuvers, the bearing error is way above our maximum acceptable error, which leads to a high risk of a lost track. The blue curve, on the other hand, well, it's still an acceptable level of tracking performance. It's at least better than the larger range corresponding to the green curve. And the bearing error during the maneuver exactly matches our maximum acceptable error, which is kind of neat. So to summarize the contributions within this optimized tracking of maneuvering targets, we've proposed a method to optimize the sensor trajectory based on the predictions of the target trajectory, and also a method to compute the optimal tracking range given that we know some properties of the sensor and the target. And this second method also works to compute the optimal beam width or field of view in case we know what range we're going to track the target at. Moving on to the final part then, planning for multiple target tracking. And here it gets a little more complicated. So we have a number of mobile sensors still with limited fields of view. The fields of view are indicated in orange here in this figure. And the number of targets are now unknown and time varying, as new targets may enter the scene and existing targets may also leave the scene. And in this type of scenarios, you need a representation of both where the detected targets are located. Here in the figure, they are marked by the orange dots. And you also need a representation of where they might be yet undetected targets. That is, targets that the sensors that are there but have not been discovered by the sensors yet. And the task that we're considering is that we would like to control the sensors in order to search for undetected targets and at the same time maintain accurate state estimates of the detected targets. That is, track the detected targets. So the input to our planning algorithm here is the estimated states of detected targets and this representation of where yet undetected targets may be located. These two entities are usually handled separately. So you take the output from the sensors and you produce tracks from the measurements. And at the same time, you take the data about where the sensors has been, combine it with a model of where you think new targets appear, and you get some kind of representation where there might be undetected targets. And you feed both of these entities into the planning algorithm. Now, a fairly recent target tracking algorithm called the Poisson multi-Bernoulli mixture filter, or the PMBM filter, is nice in that way that it treats these two quantities jointly, which means that it provides a foundation for a unified, if you will, search and track method. And the density of this PMBM, the PMBM density consists of a Poisson component then that takes care of this representation of where you might have an idea about where undetected targets may be, and the multi-Bernoulli mixture is used to represent states of detected targets. And we have mostly focused on this representation of undetected targets, which in conventional PMBM filter implementations is typically handled using Gaussian mixtures. And here you see a very simple one-dimensional example of a Gaussian mixture intensity, where the resulting intensity is in solid orange and the mixture components are in dashed orange. A drawback with this Gaussian mixture representation is that it's difficult to represent abrupt variations in these intensity of undetected targets. For example, this is typical. Abrupt variations is the standard case when you have sensors with limited field of view. So, for example, consider a sensor with probability of detection 1 that is searching for targets within this blue region. Since the probability of detection is 1, after the measurement we know that, there won't be any undetected targets in that particular area anymore. So the updated intensity of undetected targets will have very sharp edges around this field of view here. And the question is, how can you represent this using Gaussian mixtures? Well, one idea is to just remove selected components, for example, those with mean within this field of view, but that doesn't really get you close to the actual intensity. Well, it's too smooth. Another approach is to recursively split components along the border or the boundaries of the field of view, which actually works fairly well if you add a lot of mixture components. But too many mixture components make the computations heavy, basically. So it's not really feasible if you would like to do anything real time. So what we have proposed is a new representation of this intensity, which is based on a partially grid-based representation, where we exploit the Raoul equalization and split the state vector components into, well, split the state vector into two components, theta and phi, where theta corresponds to the states that are measured by the sensor. And then we can use a point mass density, point mass intensity to represent the intensity with respect to theta, and a Gaussian to represent the intensity with respect to phi. This simple trick makes it straightforward to represent abrupt variations in the intensity, as you see in this figure here. And it's also less computationally demanding. That is, well, if you have a filter with a lot of Gaussian mixture components, this one is going to be lighter, depending on the grid resolution, of course. To illustrate the concepts here, I included another animation where we have a scenario with two mobile sensors, and the targets are entering this scene from the right-hand side here. And the proposed PMBM filter is used both for the tracking and the planning. And what happens is that at first the two sensors split up, and as you can see here, some blue region has entered the figure. And that means that, well, we assume that there might be undetected targets close to the right-hand side border, and they are traveling towards the left. And the sensors first, well, there are no detected targets at first, so the sensors, they decide to focus on searching for new targets. And as there are two sensors available, they decide to split the right-hand side border between themselves and search half of it each. Then after a while, a new target appears, and it has to be tracked then. So the sensors have to agree on which one is going to track the target, and the other one, what should it do? Well, let's search for new targets. So they decide to split up, and you see that the target, which is now the sensor, which is now searching for new targets, is patrolling the entire border because it's all by itself here. And the first sensor is continuing to track the first target, and what's going to happen is that the first target is going to leave the scene, and this first sensor will then go back to this right-hand side border and search for new targets. And at about the same time as that happens, the sensor that is searching for new target discovers a new target, which is then tracked by this sensor number 2, so to speak. And I should point out here that we haven't explicitly programmed the sensors to do what they do, but they figure it out themselves based on this underlying PMBM density and the optimization problem formulation. So to summarize the contributions within this field, we have showed that the PMBM filter is suitable as an underlying tracker in sensor management applications, and also derived a PMBM filter based on, well, grid-based intensity. And the first paper is published, and the second paper is still under review. Well, that's about it. The goals of sensor management is to decrease operator workload and to increase the sensor system performance. And in this thesis, we discuss several aspects of sensor management. For example, we show that under certain assumptions, it's possible to plan globally optimal sensor trajectories. We've also proposed a couple of methods to improve tracking of maneuvering targets, and also show that the PMBM filter can be used in multi-target search and track applications. That's it. Thanks.
Thank you very much, and thank you for 2 good presentations. We'll now take a 5-minute break and get back at 3 o'clock. Okay, welcome. We're back. So next step in the procedure today is the discussion between the opponent and the candidate. So Professor Willett, could you please take the lead here and start out the discussion.
Actually, how is this going to work? Is this only me and Per, or are the other committee members going to join in when they feel like it?
So initially it would be you two, and then when you're done, they get the chance to ask additional questions. So
I mean, you don't want them to say, I mean, I was going to go through the chapters one by one. You don't want them to ask questions during those chapters, between the chapters. It's up to you. I mean, that's.
We usually don't do it that way, so if you're fine with it,
then let's do it the way you normally do it then.
Yep.
It's all good.
So,
okay.
Thank you.
Well, let me try to get this back. Sharing?
Yes.
All right, I see a Q&A here. Is that what's going on here? Somebody's asking something? Oh no, there's something in Swedish. Okay. Okay, I don't know, probably it's not relevant that I did this, but I looked through all the chapters and wrote some comments on it. I liked the chapter 2. It was a good discussion of good overview discussion of the Bayesian dynamic estimation. It was just odd that Per, you didn't put in anything about just normal Monte Carlo particle filters of various kinds. You did refer to them, but you did all these other things you went into details about, but not those. It was odd. There's something that in chapter 2, people seem, certain colleagues of mine are always frantic about this, and when we're talking about the A and T optimalities, which involve the traces, you are often adding up things that can't be added together. And to me, it's not a big deal, but I know that some people get kind of worried about it. You can't add position and velocity together. As far as I'm concerned, what you'd probably do is simply take the position components, but I just wanted to point that one out. Any comments about that?
Yeah, sure. I mean, that's a comment I've received multiple times during from reviewers of various papers. Well, I agree. It's a bit weird to add position and velocity, but then again, it is an objective function, and if you think about, like, in optimization, you might want to minimize something in meters and something in meters per second, and well, as long as you don't have to normalize them, but you should know that if you have a position uncertainty in meters, maybe like 10 meters, and the velocity uncertainty is in, I don't know, a lot bigger. Maybe I should switch that. So the meters per second uncertainty should be around 10 meters, maybe 10 meters per second, and the position uncertainty could be in kilometers. So then the position components would dominate completely. So you should be aware of that. You need to add some weight matrix.
I guess I always get kind of, I always figure it's kind of a non-event when people complain about this, because, to me, you could do what you said. You could scale one set of components. You could also just select the components that you think should be discussed, and ignore the other ones. I have no problem with it. I had there's a certain colleague who actually has an office maybe 2 down from me who was very hot on this. And there's another colleague I was talking to by email just recently who was very upset because OSPA seemed not to be clear about which way it was going in this, which to me, it was like, well, this isn't really a big deal, but.
No, I agree. But then, I mean, if you think about a motion planning problem and you want to get from point A to point B, you want to get there as fast as possible. So you want to minimize time, but you also want to minimize fuel consumption. I mean, 2 different things could be added in an objective function.
Yeah. What's going on here? Okay, sorry, I needed to get into a mode on my slideshow here. Good discussion of target tracking techniques here. The PDA was discussed well. You didn't sort of, it isn't a conjugate prior, but you kind of make it a conjugate prior by re-Gaussianizing it. It's something I always mention when I talk about that. Mm-hmm. You discussed the multi-Bernoulli RFS before the multi-targets base filters. That's fine. It's not ordering of things. I think probably you did these at the end of your thesis when you're already done. So it's like, this probably not a good reason to talk about this. There's a good discussion of OSPA and GeoSPA, and I know one of the prime people behind GeoSPA is actually on this call. He may have comments about this. I thought it was good. Those are criteria that penalize both estimation errors and like how many targets where the targets are, and on target cardinality errors, and they don't penalize target labeling errors. Because for example, if you have two targets that if you have target A over here and target B over here truly, but you mix them up and get accurate locations for the targets, OSPA at least doesn't really penalize that. That's good. I have come across, and this is not something you need to comment on, but I've occasionally talked to some of my practical colleagues, the ones involved in, let's say, missile defense, and they say, yeah, this is good, except we do want labeling. It's kind of important because we like to maintain history so that we can get some knowledge about the target identification. And that is important, but it's something you can also put it as an overlay to this problem here. And again, yeah, there we go. I was talking about the D involving units or not. Again, a different colleague kind of making making a mountain out of a molehill. That's what we say. Chapter 4, discussion of optimization. It's discussing single objective, multiple variables, inequality, equality constraints. Talking about convex functions, and then a short discussion of semi-definite programming. Hey, I have to admit, I'm not an expert in semi-definite programming. So when I read through your thesis and found that I was going to be dealing with semi-definite programming parts of it, my heart sank a little bit, but I'm able to fight my way through it. But if you're looking for good comments and strong argument about semi-definite programming, you might need to talk to somebody else. I know it's very interesting, and I know that there's some pretty cool things you've done here, particularly with the theoretical ammunition as well as the computational ammunition that these things provide you. I'm always impressed when I see semi-definite programming applied, because there's some trickiness and some real art in transforming a problem that doesn't look at it even a little bit like a semi-definite program into one, generally by adding some new variables, and that's what you've done in some nice ways. Yeah. There's optimal control here, and the idea here, optimal control is when you're controlling, when you're doing something to a system to make it perform in a certain way. Maybe you just move to a certain location, have a balance beam point balance, or have a fluid level go to a certain place. But you want to include in your criterion just not only the cost of the error and where you get to, but also the cost of the energy you expend to do it. And there's some really interesting results. The oldest one, the linear quadratic regulator, of course. But there's also additional things you can put into this, feasibility constraints. And I always think about the bang-bang control as being one of the ways to deal with that. Stochastic control, of course, is where the plant is subject to random inputs as well. And there's some discussions there about whether, I've actually already forgotten the names of these things, but the titles of stochastic control, where you use the maximum likelihood of the expected value. I've forgotten the terms, and it doesn't really matter that much.
All right.
Sensor management is a kind of stochastic control, and I think that's a nice identification you've made. The noise, the random input, is the tracker's lack of knowledge about the guidance system. I know in some cases in the past we've made some assumptions about that, like using a proportional navigation, for example. Okay, it's good stuff. Tracking accuracy is the displacement error oftentimes, and battery life is good. So I didn't comment on chapter 6 now, because it's just very short. You do discuss in chapter 6 some of the future directions, and I'll talk at the end of these slides about some things that I think are useful, and also repeat what you've mentioned as some topics for future research, because there's certainly more stuff to do. It's one of the last fallow areas, I would say, in the target tracking area, in the target tracking field.
Right.
Okay, I was very happy with paper A. It's very impressive that you can do this. I looked it up. I don't know why this hasn't been cited much. I would like you to thump the table if you can. I will try, because it seems like a really big result.
Yeah, thank you.
It may be, in terms of its citation, it's quite technical, and you change a lot of variables. And some of the variables you use are variables that I would call omnibus variables, taking into account a lot of different things.
Sorry, could you repeat that? What did you call the variables?
I call them omnibus variables, where if I remember correctly, there's like a single variable which accounts for a whole lot of different things that are going on there. I think delta was one of them there.
Yeah,
But
sure.
there's a bunch of other ones there that are there's just a lot of variables, and I think it's perhaps less digestible. People might lose not lose patience, but they would lose heart while reading the paper.
Yeah, sure. But I mean, the paper as such is fairly, I mean, as you say, it's theoretical.
Yeah.
And we don't really include any fancy application. We just say that, well, if you have problems with the type, well, you can do this. And it's...
I love it.
Yeah.
You didn't present this at the Conference on Decision and Control?
Yeah, I did.
Oh, you did too? Oh, I didn't know
Yeah,
that.
I
Okay.
did. Well,
Okay.
I had
So
the
I know that
last,
there's
I
a
think
link-
I was in the last session. I had the last session of the last day. So there was
crap.
like 5 people there, but I was there.
Oh, that's typical CDC. Well, I know that they're it's a great letter, it's a great society, great conference, but sometimes not too many people come to it. I really like it. I'm hoping that this can get more noticed. It is the fact that you have stationary targets that know locations. That's interesting. And each has a linear Gaussian property that we want. We want to maximize the information across all the targets. That's and targets may or may not be in the sensor field of view according to this delta. The ith delta represents whether we are allowed to get it, whether it's in the field of view. It's a binary variable. Nonlinearity makes convexity uncertain. You transform things to an SDP via an SDP to a convex one, and you actually have to do this for each set of deltas, I suppose.
Exactly. So if you consider delta as decision variables,
yep,
the problem is not it's not convex, but I mean for each delta sequence, you can turn it into a convex problem.
So you have to go look at all the deltas, but you actually make it quicker using branch and bound. So that's good.
Yeah, yeah, right. Exactly.
And there were some examples here. I like the examples there. There was a one where there was a place where the target could be seen from. Sorry, the locations could be seen from a single. The P's where the features are could be seen from a single location. So your sensor went there, and that's good. The other one, the sensor had to choose, sort of banging back and forth between the two regions, but spent most time at the one which was the most uncertain, and that makes sense too. I like that. I had some questions. Oh gosh, I can't remember what 3 is. Is 3 equivalent to trying to observe the target from the best viewpoint? Oh, that's right.
That's the measurement model, right?
Yeah, that's the measurement model. And in that case there, you had a constant R and I assume probably a diagonal one, and you had an H which would vary. And I was wondering if that was equivalent to maybe having a constant R, a constant H, and an R that varies. Because I would like to have inserted into this an eccentric resolution cell, let's say. Is that equivalent?
Well, I mean, you could have a constant H and set the, so let's say that you consider the covariance matrix to be, well, the measurement uncertainty to be infinite if you're outside of the sensing region, so to speak. Is that what you're after?
No, it's not.
No?
I'm looking for the radar model where you have, as I said, sort of pancakes shaped resolution cells, where you have some dimensions where you didn't see very well. And that depends on where you are. And that's kind of important when you're talking about sensor management, because if you imagine observing a target with is the pancake a good word? Do people know what I mean by pancake?
Well, do you mean that let's say if I draw like this, you have more information well, I could use the whiteboard, but let's wait with that one minute. So would you like to model that you have better measurement accuracy close to the feature?
No.
No?
What I'm getting at here is that if I observe the target from different perspectives, I would observe it with an accuracy that would change based upon the perspective. And I'm thinking particularly here, not so much of features, but I'm actually looking just at the location of this thing.
Okay.
And if you imagine that I have one pancake, so again, is pancake a word that people know? I don't know if it's just.
I mean, I know pancakes, but I'm not
Okay, good.
quite sure
So if
what
I have,
you're after.
can you see me if I'm looking, if I have a pancake that looks like this and another pancake that looks like this,
Yeah.
I know much better where the target is.
Yeah, sure. Now I
And-
get what you mean.
Okay.
So so you're after like a range bearing sensor then, instead of a.
I mean, I didn't want to be so specific, but yes,
let's
I
go.
wanted to be able to
As an
take
example.
advantage of that because it does seem to be a very important.
But I think, I mean, you could definitely model that, but I'm not sure about the convexity. I think this was a couple of years ago, but I think the reformulation is based on that you have a constant R matrix.
I thought H varied. Are you sure?
Yeah, H vary, but that you have a constant R matrix. So it's if you look at, well, yeah, as you said, I changed variables, but yeah, if you look at equation 18, in this paper.
If I look at equation 18, I'm probably going to lose my sharing here. Should I do that? Or?
Well, maybe not. I don't know how to do this. This would have been easier if you were here.
Yes, it would. What is equation 18? Maybe I should take a look.
Well,
okay,
since if you have a variable R that actually depends on your sensor state. Well, if you think about if you add the information contained in a measurement is H transpose R inverse H.
Yep.
Then you would have an H inverse of the sensor state, like you would have a matrix inverse of one of those decision variables, and that wouldn't be convex in the reformulated problem.
Oh, okay.
So that's why, you could, of course, model it. I mean, maybe you could handle it by introducing more binary variables and say that, well, you have more regions that you combine, but then the combinatorics explode. So I think it is convex in this case, but I really think it's a special case.
Okay, so that's interesting, and it is kind of important. I think it's a little limiting, but it's still very interesting.
Yeah.
Now, can you still see my shared screen here?
Yeah.
Okay, good. That surprises me. Okay. So another thing, which is a comment, but it's actually common to most of the thesis here. The kind of binary observability you have here it's a special case. Now, maybe I want you to comment on this, but give me a second here. The things that I'm more used to looking at are situations where you have let's say the radar return energy would go down as the inverse fourth power law, which would mean the probability of detection would go down fast, but gradually as a function of the distance away from the sensor.
Yep.
And I guess maybe the sensors you're looking at have exactly this 1-0 binary yes/no detectability idea. I was wondering whether you thought whether there was such an application, or whether you thought there could be something done to extend what you're doing in that direction, where you might have a range-dependent detection region. And
I see where you're going.
And non-zero probabilities of detection.
For paper A and paper B, I think this binary region that's a limitation that we need to make. But for the other papers, it simplifies things, but it's not necessary.
Okay.
Right.
It's to me, when you get to get people like some of my military colleagues reading this, I think you might want to do that.
Yeah.
Is there a situation that you're thinking of where it would be appropriate?
Where it would be appropriate to have these sharp borders?
Yeah.
Now, I was thinking about this for a couple of days ago, and I'm not sure, but what about camera sensors? Then you're either within field of view or you're not.
That does make sense.
And then you can give it to a detector algorithm, and, well, it won't, for sure, detect anything that's outside of field of view. And, well, depending on your classifier, well, maybe the detection probability is equal like constant within field of view. So I don't think that it's completely, so to speak, theoretical, but I think you could make up sensor examples which should fit within this framework.
I like that.
Although, like radars, as you say, those aren't exactly this.
I mean, there's going to be a limit anyway in terms of how far away you can see, because it gets to be sub-pixel stuff. But yeah, I think that's a limit when that's actually an easy thing to insert into what you've got. So that's good. That's a good answer. The known, I actually had to read it twice and came back to see the format of the problem. And I know you did model things correctly and exactly and explicitly. I of course tend to skim. The known location setup, where you had all the P's of where the things were, but you're trying to get a feature at those locations. That was a bit of an unfamiliar application to me, and I was wondering if you could just tell me where the sort of thing you'd be talking about there. Were you talking about power levels earlier on, something like that?
Yeah, I know it is a bit weird, I have to say. I mean, we started with the theoretical parts, and then we had to sort of squeeze in an application that would fit it.
Yep.
But you could think of a temperature sensor. That is, then you know which location it is, and you may have to go there to check the temperature at that location.
Okay, that makes sense.
Or
I
air quality, or
on it, but yeah.
Sorry.
Yeah, it's good.
Stuff like that, like things that you know have a particular location, but you don't know what is the value at some point.
This is a question exposing my ignorance a little bit here, but it looks to me as if you've turned the problem into an SDP, and you've shown convexity for this. Let's suppose that I was to try to solve this problem using solving the problem directly, the optimization problem directly from the original statement, which number I've written down there 15. Which is on I think I might have looked at the preliminary version of the thesis, so I hope my equation numbers are not.
Yeah, they shouldn't have changed. At least not for the papers. So you should be fine.
Okay. Is it true? Is the convexity and the global optimality of my solution true only once it's transformed to an SDP, or would it be true also for the original problem? If I found an optimal solution where it was clearly a critical point, would that still be an optimal solution? Is that proof? Is that something you've proven?
Well, let's see. I'm not sure if I follow, but let's say that you find a solution to the SDP, the transformed problem.
Yep.
Then you, by design, have the optimal solution to the original one.
Right.
So we start
that means
by the original.
If I didn't want to use an SDP and I solved the problem anyway.
The problem is that if you solve the original problem, which, I mean, you could give it to a nonlinear solver or something.
Yep.
But then you wouldn't get the guarantee or the certificate that you are actually at the optimal point. Well, you would get a local solution, but it could be a suboptimal solution.
So it still has it still has local solutions in it. Okay, that's my answer. And that, as I said, that's my ignorance there. But it looked.
Yeah, sure. No
I was wondering if that was the case.
The problem is that the problems of this type, well, you have to give, since it is nonlinear and it's quite nasty. I mean, the nonlinearities are quite difficult. So you really have to supply a good initial guess to even get convergence, which might be difficult in practice.
Good answer. The cost in terms of energy here, I would have expected to be a sum over K, not just on the terminal state, which is what I seem to see there. Is that correct? And if that's correct, could you explain why the energy cost doesn't involve the sum?
Well, you're still looking at equation 15, right?
I may be. I'm probably.
Because, the control energy cost is a sum over K. And then you have a term, the final term there in the objective function, it's the terminal cost.
Right.
And that we apply at the prediction horizon, at the end of the prediction horizon, and then you don't apply any control input. So that's why the U.
Got the V in there. Okay.
UN is missing in the final term.
Gotcha. Okay, thank you.
Sure.
Would this result hold for multiple sensors?
Well, yeah, I think so. The problem is that then you would double the number of binary variables instantaneously.
Yes.
So, well, it doesn't really scale. That's the problem.
Well, I'm not talking about the I'm not talking about the algorithm so much as the convexity.
Oh yeah, yeah. The result holds.
Very cool.
Well,
yeah.
the thing is that you can see the sensor state. Now I remember actually. Well, you can see the sensor state as a collection of sensors that have a joint state. So you can stack the individual sensor states on top of each other, and then the result trivially holds because it's the same problem.
Should be the next paper you push out.
Delta paper.
Nah, definitely more the delta. It's at least 2 delta. Okay, so this paper from the Fusion conference was sort of an overlay, I thought, to this one here. You are now using an adversarial observer. And the adversarial observer adds a lot of terms to the criterion. Definitely, you could see that. I think you'd agree. So I'm just wondering, just the way this worked out here, the path planning with the stealthy region there struck me that what you were doing was a lot like doing a obstacle avoidance. I guess I probably chose the wrong plot there because in the sorry about that. In the paper, in the plot that I'd intended to choose,
it's the one where it goes around it.
It was the one where you actually were avoiding that region.
Yeah.
And I was dumb, of course, and selected stupidly the wrong one. But there's a nice plot you showed there where you actually did go within the region, but the times at which you were within the region, it's actually figure 3 on the left.
Yeah, that's a discretization effect, because we only measure at these the time steps, so we don't really control what happens between those samples. Well, if we would include more time steps, we would go. Well, we wouldn't enter the region at all. Right.
So, but is there it struck me that what you were doing was a bit like obstacle avoidance. But
it definitely is.
But it was different. It would be different if there was more.
Yeah. So in traditional obstacle avoidance, you can't enter the obstacle regions at all.
Yep.
Here you can, but there is a certain cost associated with doing so.
Yeah.
That depends on your previous trajectory. Like once you have entered this region, the adversarial observer gets a measurement and presumably has pretty good knowledge about where you are. So then you can be within that region for a while without adding sort of a lot of extra cost.
That's interesting.
But in the first step you take into the region, that is costly. And sort of having a Kalman filter estimate the covariance the underlying covariance gives you like this dynamic cost of entering the region, so to speak. If that makes sense.
No, that's all good. There was a particular statement in here I kind of tripped over, and the statement you said where the true dynamics of the robot might be unknown to the adversarial sensor. Since you were sensing it, I didn't know what that meant.
Well, so the thing is that we have control of our robots, right? We know, well, it might be a differential drive robot or whatever, some kind of robot that we can control. And then this adversarial observer tries to estimate our state. So the adversarial observer does, it tracks our sensor, basically. And then it applies a standard tracking algorithm, maybe based on a constant velocity model or something, instead of our actual dynamical model. That's what I'm trying to say there.
That makes sense. And I'm about to try to insert a figure that I really did intend. Can you see it now?
And I'm only seeing you, actually.
That's a shame.
And myself.
Well, that's much better.
Not sure about that.
Can you see it now?
It's still you.
So in other words, what I have to do, I should never do this. I'm trying to be clever on this, and it's always a dumb thing to do. Okay, share screen. Back over. Yeah. Sorry about this.
No worries.
just put it in the figure that I've meant to put.
There it is. Yeah.
So, see what do we got here? The practical situation, the observability of the sensor will be affected by observation angle, I mean the aspect, and range rate, including Doppler blindness. And I don't know if this is actually worth commenting just based upon what you said, but I know I've seen some interesting, I guess you'd call it sensor management, but also adversarial target situations where a path was taken amongst adversarial sensors, to try to present as little range rate to these sensors as possible, so that you would always be in the Doppler ridge.
I see.
And that would be interesting.
Definitely, that is a related problem for sure.
Yeah.
Yeah.
Well, that's there's nothing to do with that, I suppose. It's really just a
I guess it's difficult to formulate that as a convex problem, though. But it would be interesting.
It is, but it would be wonderful to do it.
Yeah, definitely.
Or simply to explore it. Also, the examples in this paper are rather simple. Have you looked at some more complex examples for this?
Well, no. The thing is that it gets so well. If you have time to do the computations, you can do more complicated examples. But we just wanted to highlight that, well, given our problem definition, we can produce, well, reasonable trajectories. Like the sensor behaves as you would expect it to do.
Yep.
And yeah, well, no,
There's
we didn't look at more.
I'd like you to do more in the future for you know, once you graduated to send them out, because I think they'd be fascinating. This is one of the examples where I think this would be really cool. Anyway,
cool.
Paper C. This is where you're looking at tracking targets with nonlinear models, and I found it very interesting. It's in a way, it's like what you would probably do in a gut level, but seeing it laid out here is very nice to see. I stole again a figure from your thesis and put it in here, showing that basically the idea here is it's a bit like a particle filter, smart particles. I think I wrote at one point. It's the field of view is binary, of course, and the results are really good. I've written down here, key distribution is the sample possible future trajectories, optimize them stochastically based on the ensemble of these things. Branch and Brown with some pruning based upon the idea that if they end up at the same point, then you look at the one which has the best sensing that goes there. Makes sense. I didn't have so many questions. The results I wrote down quite good, but I really actually think the results are almost phenomenal. The baseline is not a bad approach. The baseline is where you take I guess, the most likely trajectory and simply to plan based upon that. And I was thinking, you know, most people are going to do that.
Yeah.
But in terms of lost tracks, it's a phenomenal what the difference is in doing something a bit smarter.
Right. And I think this baseline approach, well, the approach as such, I think it was designed for a multi-target scenario. So then you wouldn't have the sensor wouldn't have had the time to get that close to each and every target. And then that's not a problem. But in a single target tracking scenario, apparently it's not enough. Then you have to consider more uncertainties. And it's also, I mean, it's quite interesting. I mean, if you have other sensors, now we have a fairly accurate range and bearing sensor modeled. But if you would have, so let's say you have large uncertainties in your measurements, then you could include, well, not only the most likely measurement realization. Like, let's say that you have a trajectory where the target turns to the right, and your measurements indicate that it turns even more to the right. So. That's a plausible scenario that could be handled with, I mean, these type of particle planning algorithms, right?
The way I was looking at this is thinking, well, the most likely, the baseline, following the most likely path is, you know, clearly it's, you know, as it says, the most likely one, but it's actually the least informative one. So. I mean, you don't get a lot of that information by following that along, because it's kind of what you expect. And what you really want to do is look at some of the things you're not expecting.
But even if you plan your sensor trajectory only based on that most likely trajectory, it depends on your sensor model as well. I mean, if you only get bearing information, then you would get some kind of S trajectory for the sensor in order to well, as you said, a pancake here and a pancake there. If you see what I mean, right?
Yeah, you're right. And the sensor model does have does have a significant impact on it, because you can see things from sort of crosswise across the beams.
Exactly.
I was a little surprised about the choice of an EKF here. I would have thought this sort of blends so naturally with a particle filter.
Yeah, well, it does. You're right. Though, well, it definitely could have worked on a particle filter as well, and then select a bunch of particles to represent the state trajectories from those. But I don't know. At the time, I was really into Kalman filters, and I wanted to try out this UKF, uncentered transform. The sampling is based on the uncentered transform,
sure,
as you know. So, yes, it would definitely have worked with a particle filter, but now it's based on an EKF. Boring comment, but that's what it is.
No, it's fine. So I was a little surprised. The problem is it's great. Everything's good here, I think. The bibliography has some related papers in this. I'm just wondering, I didn't really catch from the bibliography represents them, but it wasn't so much discussed in the papers. And I wanted to ask you what the contribution here was with respect to what other authors have already done, and maybe those authors would include Gustaf.
Yeah, well, let's see. The baseline approach is, well, that was one of the references, right? So, and that, as it says, I mean, we extend that approach by including not only the most likely, but also other plausible target trajectories. But I'm sure, yeah, we could have elaborated more on how it differentiates from other previous works.
I have no problem with it. I just was sort of wondering about that, because I liked it, but it's kind of a person would probably come up with something. Well, maybe would come up with something like that. I'm actually looking at the next one here. Actually, I wonder what reference 9 is, but you had a comment down here at the bottom. I hope you're still seeing my slides.
Yeah, I do.
This paper extends the work of 9, which is by some authors I don't know, by incorporating the knowledge of uncertainty of the future target trajectories in the planning process. And I didn't want to look at 9 because I'm lazy. This is one by Atanasov.
Yeah, it's a bunch of people. I think they're at UPenn, I think, Pennsylvania.
Okay.
Pappas, at least there.
Pappas, yes.
And yeah, 9 is actually the baseline approach, where you ignore uncertainty and just go with the most likely trajectory.
There you go. Good answer to my laziness not going back to look at that paper. Okay. Maybe I did like this very much. I don't know why you haven't made this a journal paper.
Well, me neither. Maybe I just wanted to go to aerospace conference. I don't know.
There you go. But you didn't, wasn't it last year?
Yeah, it was, but the aerospace conference was just before the, but I remember someone didn't show up for some reason.
Me, I couldn't show up. My university wouldn't let me. Are you talking about me? It really sucks.
I know. I listened to your talk there.
Yeah, I was talking.
Over phone. Yeah.
Ridiculous. And anyway, so I remember this is done by with Dale Blair.
Yeah.
And I work a lot with Dale. There's a relation between alpha beta, the tracking index, of course. That's a fairly common thing that goes back to the original definitions of alpha beta filters. The alpha beta filter is the steady state Kalman filter for kinematic systems. That's the Newtonian systems where with position velocities. People don't know. Now, I think what you said there about not following the way the paper is written and what you were saying about not following the target too closely is, probably a better way to put it than what I was thinking of it as. But I was thinking of it perhaps more broadly as a trade-off between a spoiled beam, spoiled range, spoiled beam, and tight ones. Because if you're tight, you get good information, but you can also fall out of the beam. Whereas a spoiled one, you couldn't. And I'm thinking maybe a mixture of the two might be a good idea, but I'm not certain about that. the it is, I think, a very interesting concept here, and I know that I've seen Dale doing some similar things here. You, of course, are doing this from the point of view that if the target's further away from you, then you have the resolution cell size is larger, simply because it's further away. You have more beam width to play with, and that makes sense. So what have I got here? Paper explores the trade-offs between accuracy, field of view. Based on tracking index, there's a best kappa, which is what did I call it down there? It's the ratio between the process noise standard deviation and the maximum target acceleration, which is an important concept because that tells you how fast the target can escape your purview, and you have to go find it again.
Yeah.
There's also minimum that causes predicted position estimate to be less accurate. To be more inaccurate than the measurement, and that's a bad proxy for a bad situation where you're probably gonna lose your track. You're kind of deeply into levels of abstraction about what these various things mean. So if we can go to figure 1 there, on the paper, I just wanted to make sure didn't make sure I understand. I want some guidance in understanding it. So for the places that are feasible, with gamma D less than 0.1, right. What is the kappa I should choose? Is it on the orange line?
Well, that depends, right? If you would like to, the orange line would be the best one. If you would like to minimize your maximum mean squared error, to get the smallest RMSE during worst case maneuvers. And you can't choose a kappa smaller than kappa min, right, if you would like the bearing errors to be smaller than what did I use? A third of the beam width, I think.
I thought it was. Oh, maybe it is a third. Okay.
I thought it was a third.
Yeah, you're probably right. You did it.
It's a number, a fraction of the beam width.
Yeah. So I mean, the point is you can go above the blue line, but you can go anywhere above the blue line. I'm thinking you want to go on the orange line.
Yep, exactly. Okay. That's what you want to do.
That's what I wanted to understand.
So in Dale's previous paper, they weren't talking about they didn't relate the choice of process noise to the beam width or anything. They related it to, we don't want our estimates to be worse than the standard deviations of the measurement. Well, we don't want our estimates to be worse than our measurements. Then you get the corresponding blue curve here. So
which is a bit ad hoc, but probably pretty reasonable.
Sure.
And I did want to comment on number 4 here.
Okay.
And I'm surprised that Dale would write this, because Dale did a lot of the work that I quote. Number 4, you've got a track accuracy which is deterministic. But actually track accuracies, measurement accuracies, range accuracies, I'm sorry. And sorry, this is beam accuracies, this is angle accuracies. They're actually they're not constant. Downstairs it should be the observed SNR, not the SNR itself. Because sometimes you get a loud measurement, you get a good angular accuracy, and sometimes it's quiet, you get a lousy one. I'm not sure if it makes a big difference.
Well, all of these sensor level details are from Dale, so I'm not 100% sure, but correct me if I'm wrong, but we do make the assumption that measurements are on bore site.
Yep, that's typical.
Is it still a function? Well, is it still not deterministic?
Yeah, because using the monopulse ratio, you'll get you get an observed SNR, which is the sum, which is the SNR based upon the sum channel energy.
Okay.
One reason I'm saying this is that I do like this work very much, and I would like to see it in a journal, and perhaps an extension dealing with a more realistic number there might be a way to do it.
Cool. Yeah. Thanks. Good idea.
So I guess it was in 19. I think it's just we use a proxy for it. You're using probability of lost track there.
Yeah.
I think you're just talking about beam widths, right?
Yes, it's a bit ad hoc. I wanted to have a user defined parameter which was related to probability of a lost track.
Yeah.
instead of saying that, well, I don't want my estimates to be worse than a third of the beam width in bearing. So, and then to do that, I'd have to assume that the measurement errors are Gaussian. Well, reasonable or not? I think it's fairly reasonable. And then you could sort of use the CDF and get the number based on...
Did Dale give you the 1/3?
Yes, it did.
Okay. Yes, it's reasonable.
Yeah.
As it would be with Dale. Okay, paper E. So getting closer to the end here. The Poisson multiple filter models extant targets, ones that are already there, usual way, and counts for which, I mean, unusual. It's quite complex and quite beautiful, but it's sort of a typical thing. And it has an augmentation here where you have I tend to think of it like a PhD. That's probably not accurate, but it kind of like a Poisson random process of target birth. The Poisson intensity could be larger near the horizon. In fact, I think I wrote this before I'd read your paper F, but indeed that's kind of what would practically happen, that new targets, they don't appear randomly everywhere. They tend to appear at the edge of your field of view. And that's indeed what you model in figure, in paper F, which is great.
Yes, right. So the nice thing with this PMBM, the Poisson part, is that, well, you don't just model the intensity within your field of view, but you can model the intensity of undetected targets within the entire tracking region. And then once you get to a certain part in the tracking region with your mobile sensor, then you already know, well, what's the intensity of undetected targets within this particular area.
Negative information, very interesting. I know that Wolfgang Koch has done a bunch of stuff with that as well, but in slightly different venues, I think. More like, it's not where I expect it to be, so I have to go look for it. So this extends previous work of using multi-step planning, not non-myopic planning, not grid-based. Some of the things I've seen there are grid-based in the past. Rollouts are really key. I was going to ask you branch and bound. I think you're using branch and bound. In the rollout, I've seen I think what you do for rollout is you do simulation. And I had also seen some work, I was thinking of Chiklis's work on his neurodynamic programming, where he uses rollout, where he would use a machine learning algorithm to figure out, to try to estimate what is the likely cost going down a branch into the future. Am I right about this? Are you interested?
Yeah, well, I've read a couple of papers, but I can't say that I'm expert in this. But the Monte Carlo tree search that we're using it's not really a branch and bound method.
Okay.
But once you find you have this tuning parameter, which tells you, well, basically it's to tune between exploitation and exploration. So if you tune it to exploit and you find a really promising trajectory, you will search along that trajectory in the search tree.
Okay.
Right.
So that's at a high level.
But I don't think you cut any branches really. It's just that, well, you bias your search towards promising regions.
You bias towards, okay.
More
detail there.
Yeah.
Okay.
I think so.
I did see. I was going to say the ML overlay to that might be an interesting thing to explore for the future, because.
So is that you, instead of actually simulating the rollout, you give the current state to some network and you get the estimated value function or so? Based
on a lot of previous simulations, is my impression.
Cool. Yeah.
Haven't done it, but that's I think what's going on.
Mm-hmm.
Descriptive data association A2. I tried to take a look at this here. Do you consider false alarms and misdetections in this? I wasn't really clear, and I probably should have been.
Yeah, we do. Well, in the tracking part, we do. So in the actual tracking, we consider false alarm and misdetections. Then in the planning part, we have a stochastic problem, but we approximate it with a deterministic problem, where we do not consider any false alarms or misdetection at all. We say that, well, each target which is located within the field of view will give a measurement. But that's only in the planning part. right? So we base the planning of the trajectory based on that. We will receive measurements and not get any false alarms.
Okay. So, I mean, that
You
does
follow?
impact what it does when it's looking for new targets, if I understand correctly. Because you're assuming that every time you see a true detection, it's true.
Right.
When you're doing the search. Okay.
Well, the search is based on this intensity of undetected targets, so it's sort of separated from the tracking planning, right?
Mm-hmm.
The planning for tracking, let's see if I can find the page here. The planning for search is on it's section 4.3 in the paper.
4.3. Okay, I'm looking at the paper myself now.
Yeah.
So yeah, I'm looking only by section. I don't have the page numbers. So, yeah. Okay.
Well, section 4.2 and 4.3 discusses the objective function with respect to tracking and searching.
Uh-huh.
And in let's start with 4.2 then. In 4.2, we say that we have this approximations to reduce the computational costs, which is basically, well, we have this stochastic problem, but let's forget about the uncertainties and go with the basically the baseline approach from paper C. We say that, well, the targets will behave as their most likely trajectory indicates, and we will receive the most likely measurements. And then based on those measurements that we will receive for a trajectory, we propagate our PWEEP, the tracker, the PMBM density, and get new state estimates. And in the objective function, we use measures of the resulting covariance matrices, right? And then the search part is based on the Poisson part in the PMBM density, right? And then in the objective function, we integrate, the expected number of undetected targets within the entire area is the integral of over the intensity, the integral of the intensity over the entire area, which is equal to the sum of the weights in the Gaussian mixture. So those aren't the search part isn't really based on, it's separated but connected to the tracking part.
I'll be happy with that.
Yeah, sure.
I'm going to my third comment there. I'm just going to ignore because I think I did figure that out. I wrote down equation 39A, which let me see. I hope this is the same numbering as what you have. Let me take a look and see what that equation is. Where was I? Here we are. 39A. Oh yes. 39A is it's very compact, of course. Tells us what the density of the target is being pushed down by negative observation and springs up with time. It was really just a question I was having about this, about your notion, your opinion about stability of this. I was just kind of wondering if there was a situation, if your feeling was there might be a situation where the rate at which the new targets were assumed to reappear became so high that the sensor management got confused and started banging back and forth between tracking extant targets and finding new targets. And you probably won't have an answer to that, but I was kind of wondering about the stability.
Well, I have sort of experienced that as we did the simulations. There is a tuning parameter which you have to fine tune to get the behavior you would like to have, and which tells you what is the most important. Is it more important to track targets that you already know about or to search for new ones? Mm-hmm. And that parameter, well, you have to find a good value of that parameter. And I really would like to look into a method where you could classify the situation, like see that, well, given our current belief, it would be more beneficial for us to search for new targets, even though we have found a couple of detected ones. But in this paper, we've chosen a reasonable value, which gives good performance, so to speak.
it's natural to choose the reasonable values for your paper, but I think
Exactly.
if you have observed instability, I would think that's particularly interesting as well.
Sure.
And I think might be the subject of some future research, because that would
Definitely.
be it, because I don't think it's a problem in your algorithm. I think it's a problem in the it's a more fundamental problem in the search and track scenario that
Yeah,
you
you
probably
have,
know about.
or whenever you have conflicting objectives
Right.
and limited resources. So
And I haven't seen anybody talking about it. And if it does happen, I think it would be interesting.
yeah, definitely.
Okay, paper questions. Paper F, next page. Oh, okay. Sorry, this is what paper F is the next page of the slide. You write in basically in question in number 8 here in the PMBM paper filter implementations. The birth intensity and intensity of undetected targets are commonly modeled as a single Gaussian mixture. While the approach is suitable for the sensitive field of view, covers most of the field of interest, potentially inefficient. You're slightly diminishing the value of your own work. Is that's okay, but is that fair what you're saying? I mean, 8 is your own work.
I mean, I observed the problem, right?
Yeah.
That it gets tricky to represent these abrupt variations in an efficient way using Gaussian mixtures. So, I mean, I know that's a problem, and I didn't see any reason to hide it, so to speak, even though I'm the author of the paper that I'm saying, well, you shouldn't do like this.
Very honest. Okay. Paper F. Okay, so this is where you have the uniform one. I know this is the one that's under review still.
Yeah.
Now, I guess I was struck by. I mean, I like it and all, but it's and there's some places there where I have trouble following some of the approximations. But I'm going to take your word for it, particularly when you start in some of the operative equations. But I take your word for them. I guess I'm struck by the fact that this is an artifact of the binary model you've used for detection, and that with more gentler models, the Gaussian mixture, and perhaps even not so many Gaussian mixture components, might be the thing that you would want to use more likely.
Sure, definitely.
You might not need to do it.
That's right.
Okay.
I agree.
I mean, it is more efficient, and I do like that idea. Oh yes, pick some questions. I was surprised that you. Well, I like the way you split off the observable and that's right, observable and unobservable components in the thing you're tracking independently. Well, I'm not sure why you're not necessarily modeling them, or you say you can transform things so that they are independent of one another. I'm surprised by that.
Yep, that's one comment that we've received from many of the reviewers, actually. And the thing is that, well, it's not an approximation. It's just that I've written in this version of the paper, it's written in a weird way. It's because we're using this Rao-Blackwellized point mass filter. Mm-hmm. We know when we're about to predict, let's say phi k plus 1. Mm-hmm. We know the value of theta k plus 1, which we can exploit in the
theta you track, theta is observable, phi is not? I can't remember.
Sorry?
Is theta the observable part and phi is the unobservable part?
Yeah. Okay. Yeah. Well, observable or the state components which are involved in the measurement function. Right.
I'm sorry, you're right. Observable is the wrong word.
Yeah.
I shouldn't have used that. Directly observable.
So the thing is, you don't have to assume that the matrix Q there is block diagonal, because if it's not, then you can do the transformation like within the filter equations, because of the fact that you know the next theta the next value of theta. Mm-hmm. Which means, well, it's I think it was derived for the Rao-Blackwellized particle filter, and it's used also in the Rao-Blackwellized point mass filter. So in the revised version, I've rewritten the order of equations here, which makes it more clear. And I realize my comments now doesn't make it really clear, but
no, I think it does. I mean, basically, it's if I understand correctly, it's sort of an artifact of your implementation. you don't really need it.
Well, assuming that Q is block diagonal makes things a lot easier when you have the equations, let's see, it's 14 to 16. But if it's not, you can transform your motion model such that it becomes block diagonal and have the same structure. Well,
okay. I'm looking at 14 to 16. Anything you can do not to make those more complicated is good.
I agree.
This is not important, but I was just moving down your reference list there. At least this copy of the paper, reference 10 was not at all complete.
Not at all complete. Wow.
Reference in its citation.
I see. Well, that should be corrected. Yeah.
Okay,
well,
so
that's a shame because that reference is fairly important for the paper. So
it is. So shove it in there.
Definitely. Thanks.
So in 28, I wrote down here, what are the terms in 28? I think it's just where you have the two, you basically very briefly say, I've got these two things I'm adding together, and I'm kind of wondering if you can tell me what those are.
Well, we're using, it's the same objective function that's used in paper E.
Okay.
And so for this paper, we see the sort of derivation of this, equations, what is it? Well, the prediction and update steps with the grid-based intensities. That's the main contribution of this paper. So we sort of said that, well, the sensor management part is not really a contribution, but we use this model to highlight the applicability of the method. And then we figured, well, maybe we can just refer to another paper on why we chose this objective function. But I think it makes sense to explain a little bit more. It's very brief.
Self-contained is always good if you can do it without a lot of cost.
I think we have enough space to do it as well.
Yeah, well, there's that. And don't like to pay overlay page charges. So what's different about the formulation here? This is the first time I've seen multiple sensors.
That's right. And
what's different here?
There is no difference. It's just that for I don't know. I thought it was fun to include more sensors, so I did. But there's nothing in paper E that says that you can't.
Okay.
Except that, well, maybe the computational cost is too high due to these Gaussian mixture models.
That's fair. Well, for your sensor model, yeah. Okay.
For my sensor,
yeah. Okay. I'm basically done with all the comments here, but I wanted to spend a couple of minutes, and it seems like, well. Gustaf, is this reasonable? I've got like 3 slides or 4 on like things I think might be done in the future. Should I go through those now?
Please.
Okay.
Go ahead. Yeah.
So then I will. There's got a couple slides here. Things that I thought were for the future. In chapter 6, there's a nice discussion of future. You talk about decentralized sensor management where they're not communicating. There's no central planner. Very, very important, very interesting, and very complicated. Adaptive sensor management, where sensors learn perhaps on what's happened before, where the targets are likely to appear. And I noticed you were talking about something which probably I may be wrong, maybe of interest to your employer, that there's an application of an undetected target intensity process to driverless cars. Makes sense. Additional topics, I wrote down a bunch of them here. There's I guess I talked about this before, the range dependent detection probability, R to the -2, R to the -4 law, for example, possibly the swirling model.
Yep.
Aspect dependent detection probability. That's for radar, that's really important. If you get something broadside, you can usually see it quite well. And if you're not broadside, you often can't. There's I didn't see very much about false alarms, but that could be my sort of high level reading. I just would think a bit more false alarms in there. I was kind of struck at one point. I know there's a branch of mathematics here, and I've seen some things on it before, called, I think, search theory, and the methods particularly in papers E and F, but also the other ones too. I was surprised not to see the names Washburn or Licata in the reference list. There probably are the ones there. They're the ones I associate. I wrote down here, actually stole it from the website, the Metron thing. I don't know if you remember Air France 447. They were looking for it.
Yeah, I remember. Yeah.
They found it based upon some pretty detailed and very kind of cool mathematical models about where to look. It's hard to look in the bottom of the ocean, and they these guys at Metron, if I understand correctly, they kind of guided the research. Sorry, the actual searching
Right.
people, the UAVs that went down there.
Yeah.
Based
Didn't people do the same
testing where it
for? Oh, sorry. Didn't people do the same for this Air Malaysia MH something in outside of Australia?
I don't know if they did it or not. I know I've seen a lot of work done by Neil Gordon on this. I think there's some additional things, but I almost think that they sort of tried, but they realized they didn't have a good idea based upon the fact that unlike going on a flight plan, it clearly took a diversion, and they're looking at some weird Doppler shifts on observed by the satellite to infer where it might have been.
Yeah.
I just don't think there's enough info. But you're right. They probably did look at that problem and didn't do anything with it.
Mm.
But there is a connection here. I mean, the way they tend to look at the world is like, well, I think I've stolen this from your on the diagram on the left there from your thesis, but that is very similar to the way they look at the world when they're doing searches as an occupancy probability that gets pushed down. In search theory, I think they typically just look for it as a static thing, but they also are interested in looking at it with a dynamic thing where the things move up. The occupancy probability moves up after a while through birth, and it seems like a useful connection to make.
Right. I will look into it.
Washburn is I'm sure I'm wrong with the references, but Washburn's the name I come up with in my mind as sort of the prime original promulgator of this stuff. But I saw a bunch of stuff by Jean-Pierre Lecadre a bunch of years ago where he did some really neat stuff with using this for some practical situations. Game theory, I was going to say one can assume that targets and sensors will try what I think would be an Ash game. That the targets are, in the thesis is assuming the targets are non-reactive and sort of dumb, really. They're just doing what they do, as opposed to knowing they're being tracked and trying to avoid being tracked.
Right. Or in a rescue scenario, like try being found, right? So
yep.
Yeah, that as well.
It will be interesting if your targets were of differing value. That does happen quite a bit in practical situations. I'm thinking of missile defense, where you probe what you see as a bunch of targets until you see there are mostly garbage things, which you kind of tend to ignore, and then you pay attention only to the things that might be warheads.
Right.
And that's usually arises with time. So it actually is a joint target ID and tracking problem.
Exactly. Well, these PMBM filtering, or the RFS-based methods, what they're doing, well, I think one of the guys in the committee has done a lot on this, but they're estimating basically snapshots of what the scenario looked like, and there's no formal connection between two different time steps. So you have to add some additional layer to produce trajectories, right? But there are methods that produces trajectories, that is, like, without introducing an ID, you get you get an implicit ID because you estimate the entire trajectory using this PMBM, tracker instead of filter.
Well,
version.
You might incorporate labeled multipernalities in there too, right?
Right.
So there is a concept of target spawn, which is important as well. And particularly, I think I mentioned this before, but in military applications, you're worried about submarines not just being themselves, but launching torpedoes and warheads dissolving into multiple warheads and a lot of other things. And that's interesting. And one of the things that comes up there very strongly is the resolution. Particularly if you have multiple sensors, you would like to have often to be able to look at different perspectives downrange where you have better resolution of what's going on. Because if everything is in the same pancake, then you can't really see very well what's going on.
Right.
And there's also an idea here about sensor management. There's going to be, I think, a special session in AES coming out soon. Well, I know there is, on goal-driven targets and trying to use the information about where the targets might go in your tracker. So, for example, in ocean targets, they're probably going to a port, and they're likely sticking close to sea lanes. And if they don't, then you definitely want to take a look at them. Missiles will probably seek out high-value targets on your side. and that's, clearly you're gonna want to use that information as well. If I got any more here, no, that's it. I am done.
Good job.
Thank you very much. It was a discussion that I really enjoyed.
Me too.
I'm gonna stop sharing now, if that's okay.
Sure.
You stop me.
Perfect.
Good. Okay.
So thanks a lot for that discussion. It was insightful, and I think it was some really nice questions and answers there. So let's go on with questions from the committee. Usually we let the member who traveled the furthest to come here start.
Leonard went all the way from his living room to his bedroom.
Yeah, it's slightly tricky today, but let's start in Gothenburg. I think that's the furthest away. Professor Svensson, could you please start?
Sure, thanks. Yeah, I'm in the kitchen, so yeah, it's been a long trip. All right, thanks for inviting me. It was an honor and a pleasure reading the thesis as well. I will just, I focused my questions on paper E and F. My first question regarding paper E is actually if you've considered using reinforcement learning to tackle the problem.
Well, we haven't done it, but we have definitely thought about it. I think the problem as such is very, very suitable for a RL approach. And one of the benefits with doing so would be that, well, we could include a sort of more complex, if you will, objective function. Well, instead of just including a measure on the covariance matrices, we could say that, well, the track length or so could be included.
Yeah, so that was my follow-up question. Could you elaborate on how you would do it then, if you're not sort of restricted to?
Yeah, well, I could take the example from paper C, maybe, where we have this. One sensor is tracking one target and it maneuvers, and we would like to not lose track of it, and at the same time have an accurate state estimate. So what we do is we penalize large covariance matrices. But what we're really interested in is to not lose track of the target, right? And if you would have a RL approach, I guess you would have in the reward function, you would say that, well, in this simulation, if I apply this policy, I was able to track the target for this amount of time, which if that is a long amount of time and I during that time produced accurate state estimates, then that would be a good policy, so to speak. And that would...
So would you more or less use something like GOSPA integrated over time, or maybe a trajectory estimation version of it, or something like this?
I guess that could work, because then you, since you're running simulations, you have access to the ground truth, so you could do it, right?
Sure, yeah. So do you have any intuition regarding in which scenarios that it could make a difference then?
You mean applying reinforcement learning in which scenarios?
And
the GOSPA objective function,
for instance, right? Yeah.
Well, so the objective function in paper E and F is, well, it's GOSPA inspired, so to speak, since we're penalizing the covariance matrix, the trace of the covariance matrix. Well, it corresponds sort of to the estimated mean squared error or predicted mean squared error, and the search part of the objective corresponds to the number of undetected targets, which at least for some values, so the parameters in GOSPA is the term in GOSPA.
So when would it make a difference then?
I don't have any good answers to that, actually.
Right. But I guess, one of the approximations that you make there is that you say, if it has been detected, it will always be detected as long as it's within the field of view.
Right.
So
in scenarios with low probability,
assuming that the field of view is very sharp, right?
Yeah.
Such that it's either in or out. Right?
That's what I do. So in scenarios with, well, not that sharp edges around the field of view, and also if the probability of detection within field of view is not close to 1, but rather like it's 50-50 whether we get the measurement or not. In such situations, I guess the GOSPA-based reinforcement learning method could make a difference. And also if there are lots of misdetections, or not misdetections, but false detections that you would like to consider in your planning, which I don't, based in paper ENF at least. But then I haven't done that much reinforcement learning, so I'm not sure about how it would scale to handling, in the scenario in paper C could definitely be handled using RL, but more complex scenarios with more representative sensors. I don't know. Maybe it could be done. I'm not that experienced in the field, so I can't say.
Yeah, I think it can.
Would be interesting to try it at least.
Yeah, I think so too. Sort of a semi-related question. Are you familiar with the concept of recycling within the PMBM?
Yes, I have read the PMBM papers, so yes, I am. Well, you have to correct me if I'm wrong, but I think that is the case when you have a track with really low probability of existence. So instead of considering it as a track, you put it into the undetected intensity.
Yeah, exactly.
Basically.
So you have detected objects or targets, if you want, that you represent using Bernoullis, and then you have undetected ones represented using Poisson point process. Mm-hmm. And then if the existence probability is below some sort of threshold, you would go, this can actually be approximated very accurately using a Poisson point process. So you pretend that it belongs to the set of undetected objects instead. So as you said, you remove it from the multi-Bernoulli and you put it into the Poisson point process instead.
Right. But yes, do you think that could be used in the planning setting somehow?
Yeah, so I guess I'm wondering about. So there are a few. Actually, by the way, Peter Willett mentioned the PhD filter a couple of times, and there's a very elegant connection between recycling and the PhD, in that if you increase the threshold to 1, and you actually recycle everything in the PMBM filter, you obtain the PhD filter.
Also, because in the planning, in the optimization problem that we formulate for the planning, we ignore targets or tracks with too low probability of existence. Exactly. So, including those in the undetected intensity of undetected targets would be a way to sort of not ignoring them, but.
Yeah, exactly. So that's so. How would that change things? You think?
Would it be, I'm not totally sure. Well, one thing is that if the sensor is in an area where we don't expect to find any undetected targets, but we get a lot of false detections that we start up new tracks for, maybe I'm not sure where I'm going with this, but those tracks that we then, we set up new tracks based on these false detections, but we ignore them in the planning context. Those tracks wouldn't then be ignored because they would have been immediately recycled into the undetected intensity.
Yeah,
and
I think
I'm sure that
in the extreme case that you were sort of mentioning here, where you don't expect to have any objects in a certain region, and then you get false detections there. I mean, if the Poisson intensity is almost 0 to start with, the detections you wouldn't start tracks on those, right?
Right.
However, if you have been tracking an object and then you lose track of it, so you miss a couple of detections.
Yeah.
Maybe because the probability of detection is not 1.
Right.
Within the field of view, which could be the case. In that case, the existence probably would shrink, right? And then it would be recycled. Right? Whereas in your case, once it drops below a certain threshold, you throw it away.
Yeah, that's right. And I've experienced that during the simulations that, if I miss a couple of measurements, the target is, it's gone because the probability of existence is too low. So then we don't care about that track anymore, and we move over to something else. Whereas if we would have tried to get one more measurement, well, we would probably have found it again. So that could be a way of sort of trying to find lost targets once more.
Yeah,
Interesting.
I think so. Yeah, I hope so.
Interesting comment.
Yeah, I'm also wondering if how sensitive you think that the planning algorithm would be to this threshold then if you do recycling. Anyway, so maybe a side question, but I'm wondering if you could maybe increase the threshold. I mean, it would be nice if the algorithm could behave gracefully if you shift it. Right? Such
I
that
see.
it's
Yeah.
sensitive to the threshold.
I don't have any intuition for how it would behave, though.
But anyway, you would still put some priority on keeping track of it, right? It's just that it ends up in a different part of the loss, right?
Yeah.
Yeah. And I guess if you were to use something like GOSPA or some metric like that, it would sort of handle it identically, I think, if you move it or not.
Right.
So I like this that paper and the contributions there.
Thanks.
I was there were some parts that I was a bit. I guess I should maybe only ask one more question. So I'll ask you to elaborate a bit on some of the equations in paper F that I didn't really understand.
Wow. Okay.
We'll end with a more boring question, I guess.
Don't worry.
Well, I guess it's sort of the update step, page 187, at least in the version that I have in front of me.
Yep, I got it as well.
Potential targets detected for the first time.
So there were equation number.
Well, there are several equations that I was a bit puzzled about. 22, maybe in particular.
Yeah. I think there's an error in 22, for example. There's a scaling factor missing.
Okay.
Well, that could be one of the reasons why you think it's weird. So what I'm trying to do is to approximate this partially uniform. Well, not partially, but this grid. The left-hand side is a grid of a union of discrete, constant. A union of several uniform distributions, disjoint uniform distributions, and I'm trying to approximate it with a single one. But I think I got the scaling wrong there.
Normalizations are off, right? So,
yeah.
Anyway, still on the same page. I was curious about 24 at least. So could you explain when 24 is accurate and what the interpretation is of 24?
Well, good question. Well, let's see. Well, the determinant term there is, I agree. I see. I think it's a bit weird as well. So what I'm trying to say that I would like to compute given that I have obtained a measurement, right, at the ZK, I would like to take the measurement likelihood and transform that into a state, an estimate or a distribution over the state component theta. So if H is invertible there, which it should be according to the assumptions, then we can apply that theta is H inverse Z, right? So we basically just invert, if you will. It's a bit strange, but we do a change of variables in the Gaussian there. So I guess if the H matrix is the identity matrix, it's not an approximation.
I think that in general, leading up to this 26 equation there. My interpretation of what you're doing there is that you're saying grid cells are kind of large in comparison to the accuracy of the likelihood. So when you receive the measurements and you would like to create a new track, you don't really need to care about the Poisson point process intensity, because the posterior will be determined by the measurement likelihood.
Exactly.
Well, in that,
yeah, exactly. So if the measurement likelihood sort of falls within one grid cell, this should be the right thing to do. But if it's not, I think there are better options. And we actually received a couple of really good comments on the paper, suggesting to use the update step of the RBPMF filter, and then after the grid-based intensity has been updated, we can approximate the grid-based intensity with the Gaussian, and then get the track initialized using that Gaussian. So that is actually what we're going to use in the revised version.
Yeah, I think there might be different cases, right? Depending on how accurate the measurement is in relation to how informative the Poisson intensity is, the update should or could be handled differently. Right? At the moment, you seem to assume that the measurements are very informative and the Poisson point process are not so informative.
I think that's a consequence of me reading the reference paper number 10 or so, that assumes that the intensity of undetected targets is completely uniform in the entire space. Yeah. And I wanted to use that, so I had to approximate the grid to get there. But
it took me time to understand digest those equations.
Appreciate your time.
Thanks for answering the questions nicely.
Thank you.
Thanks for the questions. So I think Stockholm is the next closest to Linköping. So Professor Ögren, please.
Thank you, and thanks for inviting me. I really enjoyed reading your thesis.
Thank you.
First, a comment on what was said earlier about connections between Monte Carlo tree search and reinforcement learning. So this was investigated to some extent by the Google DeepMind guys in their AlphaGo paper, where they actually use the value function of reinforcement learning instead of the simulation rollout. So that might be.
And they seem to do quite well, so I guess that worked.
Yes, right. I noticed that too. So regarding the Monte Carlo tree search, the algorithm, you have the rollout, and as I understand it correctly, you write that you alternate between two rollouts, one being random and one being fitting the next. The other target with the worst uncertainty.
Yeah, that's the random rollout is of course random, and the other one is a heuristic approach. So, based on my intuition, I would say that, well, as a designer, I say that, well, I know that going towards one of the targets that we have, that we don't know exactly where they are, well, we are uncertain about, it should be a good approach to go towards that target. So I sort of bias the search towards doing so, and that saves. That makes it possible to find, well, to get a good behavior, if you will, without running too many Monte Carlo iterations in the search process, right? Because the solution is likely to be like close to that branch.
So when you say you alternate between those rollouts, is it first one, then the other, then the first?
I think that was how we implemented it. Yes.
So, and
well, we start from the root with one policy, right?
Yes.
And then you do something, tree search and rollout based on that policy.
Yes.
And then you restart from it.
I believe you do the rollout.
Sorry?
So you only do rollouts at the leaves of
Yeah,
the-
exactly.
Yes.
Yeah, and for each rollout, it's based on one of those policies.
Yes.
Yeah.
So it seems to me, because you're trading off tracking and searching, right? So now you have a rollout that basically does tracking.
Yeah.
Isn't it unfair that you don't have a rollout that does searching?
Yeah, maybe you're right. Yeah. It would be interesting to include another rollout which is biased towards going to like the point where we expect to find most undetected targets, or maybe the area to be fair.
Yes. So let's see. And also, so in the so you have this theme in the last couple of papers of kind of handling the trade-off between search and tracking. But it seems in paper F, it's quite binary. I mean, one agent is really doing tracking like this, and the other dude is kind of searching the border.
Right.
And then they kind of switch.
I think that's the consequence of the scenario with one single target present. Well, in the beginning there, where one target was present, and we had two sensors. Well, to maintain accurate state estimates, we need to really track that particular target. Otherwise, the covariance matrix would blow up, and we would get a huge penalty. But we still have to search for new targets, and as new targets only appear from one of the borders, one of the sensors. It's enough for one sensor to traverse that border and still have the possibility to detect any of the newborn targets. So in a more complicated scenario, maybe depending on the tuning parameter, of course, but the sensors might decide to track the target for a while, and then as it approaches the left-hand side, maybe search for targets near the left-hand side border now instead.
So if you kind of saturated your resources.
Yeah, exactly.
Throwing in, so having two found targets going across, and then the border unexposed.
Right. So depending on the tuning parameter, the sensors would either ignore one of the targets, or potentially both, or completely ignore searching for new tracks. And that is scenario dependent, I guess. So it would be really nice to sort of automatically find a reasonable trade-off there. Well, a reasonable value for the tuning parameter, because that tuning parameter definitely changes the behavior. But I think that's a really difficult problem to automatically find something.
Yeah, I mean, to some extent, it's unclear what the optimal solution is. But it would be interesting to see a simulation where it has to choose rather than stick at this, fairly clear division of work.
Sure.
Just a thing in figure 7 on page 171.
Yeah.
So between in the middle row there, between 1,500 and 2,000, you have the proper page?
Could you repeat?
Yes. So I was just checking that you're at the same page as me.
Yeah, I got the right page here, and the middle row,
yes,
between 1,500 and 2,000.
Yes. So in the far right, the blue markers kind of get weaker, even though there's no one searching there.
Yeah, I noticed. That's a bit strange, because it's then in the lower row, again, it's a bit deeper blue in the right-hand side, right? On the far right. I wonder where that is. It should not, depending on the model, of course, because depending on your probability of survival, the intensity of, depending on the level, the relation between the probability of survival and probability of target birth, the intensity at a given point might decrease even though we don't observe anything there.
Because of that, so to say.
Yeah, but I don't think that is not supposed to happen here. So I think there is, it's something weird there. It might be the print, but probably not.
It's fairly static in the first three.
Yeah, and then again, if you look at the, well, lower left, you see the two dots in the upper right corner and the lower right corner. They are again quite dark if you compare at least to the 2000 seconds snapshot. So there is something weird with the snapshot at 2000, I agree.
Maybe
They should be it should be a deeper blue, more similar to the 1500 seconds snapshot on the 2000.
What I was thinking. So, and I also like kind of paper F, of course, on the same theme, but on more of a grid thing. And just, I mean, you work at Saab, but what I imagine the Saab people would want is to get this even more applied. Imagine you have kind of a map, and then you would like to, for instance, where there's a road, this uncertainty would spread faster. And if there's a mountain, you would want it to not spread so fast.
Yeah, sort of a state-dependent motion model.
Yeah, for
right?
the bad guys, so to say.
That is something I really would like to look into. I haven't done it yet though, but I think that would be a promising direction to go. Because in many situations you know that, well, cars, for example, they tend to move on the road.
Yes.
So if you looked at one stretch of road and you didn't find anything there, well, down the road further on, well, the minute after, you probably won't find anything there either, because then the vehicle that should be in there would then have been in the previous location before that. And that could be beneficial to take into account when planning your actions.
Yeah, I think so. From kind of this search perspective, I think that's what people, practitioners, would do.
Right. Yeah, definitely.
And also, so another aspect on the kind of application side, you might argue that targets are easier to see on a field.
Easier to
spot.
Yeah.
There's a forest and there's a field.
Right.
So do you search the field because it's easy to search there? Or do you search the forest because that's where they're hiding?
Good point.
So,
you can make this as complicated as you want, right?
but I think I really love the formalism here. So I think these kind of important problems are within reach, or wouldn't you say?
Well, I think there's some work to be done before we can deploy this in an actual autonomous system, but sure, we are getting there, definitely.
Good. So that's my question. Thank you.
Thank you.
Thank you very much. So let's move closer to Linköping and go to Norrköping. Professor Polishuk, could you please continue?
Sure. Thank you very much for inviting me. I really enjoyed reading the thesis, and it also was a pleasure to listen to all the discussions so far. In fact, some of the questions that I had were already answered or at least raised. So just also to give you some estimate of the time, I have about 5 questions, and some of them are light, and maybe you will even find them fun. But I will start from kind of more complicated and technical questions, going into some things about the complexity of the problems that you've been solving. And I'm not looking at them from any kind of reinforcement learning or machine learning side. I'm not an expert in learning, other than I was happy to learn a lot of things from the thesis. But really on the computational complexity. So one particular place I may draw the attention to is on page 70 in paper A, I guess it's page 84 in the PDF document where you have equation 7 or the problem 7.
In paper A, equation 7,
Paper
is that
A,
it?
equation 7, yes. So it's
Yes.
actually the last paragraph before the modeling section. And there you are saying that, well, this problem is due to nonlinear equality constraints reflecting the evolution of the matrix and other things, you have it as a optimal control problem for a nonlinear system. Okay, I agree with that. What I have a question about is the next sentence where you're saying it is thus a non-convex problem. Could you explain this thus? Where non-convexity follows from? Non-linearity?
Yeah, well, so if you have an optimal control problem and you have nonlinear dynamics and you have equality constraints, well, the state at time k plus 1 is a nonlinear function of the state at time k. And then you have a nonlinear equality constraint. And according to the definition of convex problems that I use, the definition that Stephen Boyd uses, if there is a nonlinear equality constraint in the problem formulation, the problem is non-convex.
Got it. I see.
That's
so nonlinear equality constraint, right? Well, I mean, okay. So I wonder if Stephen Boyd has a different definition of convexity than others do. What is the definition of a convex problem?
What it is? Well, if you go to page, let's see, page 38,
You must
39. 39 it is.
Mm-hmm.
So equation 4-6 at page 39.
Right, 39. I learned that there is a shift in the numbering of the pages.
Yeah, it's very annoying.
In PDF. But I'm getting there.
Sure.
What's the equation number?
4.6 in chapter 4, section 242.
Okay, well, the equation by itself is, of course, just an optimization problem. Or, yeah.
Well, a problem is classified as a convex optimization problem, depending on the objective function f0 has to be a convex function, and the inequalities has to be defined by convex functions less than or equal to, well, 0 or any number really, and the equality constraints, well, they have to be affine or linear. That's Stephen Boyd's definition. I think there are different definitions out there, but well, I would argue that on convex optimization, Stephen Boyd is the name to go to. So
yeah, I agree. Great. Still, I was this definition that doesn't disagree with the definition that I know, that a problem is convex if the feasible region is convex and the objective function.
Right.
And I understand that nonlinear inequality constraints make you, well, the feasible region is no longer convex.
Yeah.
So that definitely answers my question. Okay, so then going back to paper A, around the same place, so it's page 72 in the paper. And there you have equation, well, again, optimization problem 15.
Yep.
And after stating it, you're saying that it is an NP-hard mixed integer program. So again, what is an NP-hard program?
Well, good question. I mean, I have to say that I'm not. Well, if I'm not mistaken, I think that mixed integer problems by definition are NP hard, but I'd have to check that. I can't promise you that that's correct. Although NP hard means that you can't solve it in polynomial time.
That's right.
That's what the difference about. That's what NP stands for, non-polynomial.
Right, non-deterministically polynomial. That's right. Well, I mean, the programs are not necessarily hard. It's the problems that can be hard or easy at the time solving.
Yes, yeah, sure.
And indeed, solving a mixed integer program is an NP hard problem in general, but maybe your particular problem and the particular program that you formulated it as is not NP hard. So that still there still needs to be a separate proof that your particular special case of mixed integer program is hard. You can formulate anything as a mixed integer program, short as fast as a mixed integer program. It doesn't make it.
Yeah, I see what you mean.
But it's okay. It's important that I also understand what you mean. And of course, I give it to you. The problems you're considering are definitely hard to a certain extent, which brings me to my next and final hard question. And it's kind of general. I see it in similar statements in two papers, in paper B on page 84 and paper C, page 102. So I don't know which one we should go, but I have the citation also. So you're speaking about computational complexity of solving POMDP, partial absorbable mark decision process problems. And the particular sentence is that the computational complexity of solving POMDP problems is considerable. And in many cases, yes, there are, and then you have different wordings. And again, my same question is, what do you mean by considerable?
Well, the honest answer is that, well, I know that they are difficult to solve and it takes a lot of time. And I mean, POMDPs are often formulated as, well, I would like to get the optimal policy, which is, well, return these for each state, for each given state, I would like to have the optimal action, right? And if there are uncertainties involved, you don't get, well, let me rephrase that. Well, MDPs try to get the optimal action for each state, which is doable if you have a finite number of states, I guess. But POMDPs, well, you don't have perfect information to start with. So you have a distribution over which state you're in. And to compute the optimal action for each possible distribution of the state. Well, how would you even do that? Because the distribution of the state is a continuous variable in some way. So you have an infinite number of possible distributions representing the state. So it's impossible to compute unless you get a closed form solution, which is possible in some cases.
Right. I mean, that's probably a more precise answer than just saying that POMDP, the complexity is
definitely
considerable versus unsolvable, intractable, and in what sense? I guess one may be more precise.
Yeah.
So I guess if it's not possible to solve POMDP at all, then maybe that voids my next question. But I will ask it anyway. So okay, if I understand correctly, what makes it hard is that there are many states, many variables, and so on. But potentially for a small number of state actions and the variables in general, you can solve it to optimality. And I was wondering whether you had any kind of experiments where you have a small chain or the state process, the POMDP, and then you can actually solve it to optimality and then compare your heuristic solutions to understand how well they are doing.
Yeah, a good point. I haven't looked into it, but it makes sense to do it, I would say, yeah.
Well, if it's possible, because as you say, if it's not possible.
Yeah. Well, It would have been nice. It would be nice to apply I think the results in paper A and paper B, since then we can, for those problems we can guarantee that the optimal solution can be found. It would have been nice to use a heuristic approach on similar problems and then obtain the optimal solution using paper A or the method in paper A, sort of, and evaluate our more practically applicable method to the certified optimal solution. Well, I think that's sort of what you're after as well.
Yeah, I agree. It could be a very nice application of result specifically.
Combining the works, so to speak.
As a baseline. Okay, my next question would have been that I wanted to look some videos how things are evolving, but you already answered it. Thank you for your own presentation. And my last question, it does refer to page 23 in the thesis, but you don't worry too much about scrolling there. You given a reference for logarithm being an increasing function. And I think you're underselling your thesis, because most of the times people who read your thesis would probably know that logarithm is an increasing function. But it's still nice, yeah. And the next reference is a kind of type 2 error. That's not an error at all. That's all I have. No more questions. Thank you very much.
Thank you.
Thank you very much. So we still have our reserve. Professor Åslund, do you have any questions remaining after this?
Yes, I just have a short question about the theorem in paper A and B.
Yep.
You consider positive definite matrices there?
Yes.
Does the result holds if you consider general symmetric matrices?
I think, there should be no, I don't think it holds. Not for all objective functions, because I think you can construct a objective function which gets you a really low value on the negative definite cone.
Okay.
And then it's possible that it's unbounded from below if you do that. So it's a bit sloppy. It should say that we consider x to be in the positive definite cone. The theorem.
Yeah, that was my comment too.
The thing is, we started with covariance matrices and information matrices, which by definition are
I understand
on that side. So
you apply it, so it's kind of natural that's okay.
But yes, you could construct an example where you would get a negative definite optimal solution.
Yeah. But if you remove everything about positive definite in the theorem and only consider symmetric matrices, I think this theorem holds then.
Yes, but you have to remove other things as well. You can't then the assumptions are not that the functions are matrix decreasing on the positive definite cone.
Yeah, if you remove that too.
If you remove all of those, then it holds.
Yeah.
Yeah.
Because I looked at the proof and I didn't see that you used the positive.
Yeah, the thing is that there are quite few matrix decreasing functions on the whole symmetric matrix space. So we didn't want this. We wanted a theorem which we could apply. So we constructed it in that way. Yes.
Yeah, that was my only question.
Yeah, I see. Thanks.
Thank you very much. So if there's no more questions from the committee, I'll move on to open up for the floor to come with questions. And please state them in the Q&A function. And Daniel's co-supervisor will read them to us and we'll do our best to answer them. Do you have anything incoming?
No, not yet.
So while we wait a couple of minutes, let me just thank everyone involved so far for your involvement and your interactions here, because I think we had a really nice afternoon in Sweden so far. Getting any?
No, nothing.
I think we went through the thesis really well in the part with the opponent and also through the committee's work. So if there's nothing coming in right now.
No, it's still empty.
So then I'll actually declare this public part of defense over. And if the committee and the opponent could please join the other decision meeting, and we'll make a decision there, and then we come back here and announce the results in a while. Okay, we are back. We had a committee meeting and we elected Professor Petter Ögren as chairman, so he'll deliver the result.
Thank you. Yes. So Per, we meet again.
Yes.
I would like to say on behalf of the committee that we were very impressed with your work. So just keep it up. And so the decision, which was unanimous this time, we all voted for passing you. Congratulations.
Thank you very much. Thank you so much.
Congratulations, Per. And
Tackar.
And a small.
Thank you very much. Thank you so much.
So I think that's the end of this defense.
I just want to say thank you to the opponent, Professor Willett, for accepting to act as the opponent, and thank you to the committee for doing a great job as the committee. And also thank you to Gustaf and Daniel, and to all of you who have watched this event at home. Hope to see you soon.